We have an example where we want to launch a 1,000 kilogram rocket from Earth, assume a static Earth. How fast should the rocket be launched in order to escape Earth's gravitational field? Okay, so we're basically launching something from Earth. We want to figure out how fast do we have to launch it, assuming no more acceleration, so that it will escape Earth's gravitational field. That's the escape speed. And so we'll just draw a picture of Earth. And we're going to launch this rocket from the surface with some velocity, v escape, VE. And so in order to figure this out, we know that if we want the minimum, the minimum speed required in order to escape Earth's gravitational field, then what we want to do is set infinitely far away. We want to set the potential due to gravity equal to 0. And if we want to just barely make it out of Earth's gravitational field, then we also want to set the kinetic equal to 0. So both of those will be 0. Okay, so if we apply conservation of energy, we're going to have E initial equals E final. So once we launch the rocket initially, there's no more external forces in order to push it. And so all the initial energy is going to be kinetic plus gravitational potential, and there is going to be 0 energy infinitely far away. So that's 0. And then we can solve for kinetic. So kinetic initial will be equal to the negative of gravitational, which is equal to the negative of negative g mass of Earth, mass of our rocket, over, so how far away is it initially? Well, it's at Earth's surface, so it's going to be a distance of r e, meaning radius of Earth, away from the center. So we'll put a radius of Earth right here. And then we can go ahead and get rid of those negatives right there, and then we'll replace kinetic with 1/2 times the mass of the rocket times the escape speed squared. G, mass of Earth, mass of the rocket over radius of Earth. And then solving for velocity escape, these masses cancel out. That's the mass of the rocket. So the mass of the rocket actually doesn't matter. And solving for velocity escape, we get 2 big G mass of Earth over radius of Earth. And we'll square root everything. Okay, and so here are the values for the mass of Earth. Mass of Earth is 6 times 10 to the 24 kilogram. I just Googled these values. The radius of Earth is equal to 6.4 times 10 to the 6 meter. And if we plug those values in, so velocity escape is equal to 2, big G is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared, times that by mass of the Earth, so 6 times 10 to the 24 kilogram, and then we're going to divide everything by the radius of Earth, which is 6.4 times 10 to the 6 meter square root. All of those things, plug that into your calculator, and you end up with 11,200 meter per second. So pretty fast. And just for a little bit of practice, so just a short assignment, try to do the same thing. Find the escape speed if we were on Jupiter instead. So find the escape speed from Jupiter, and then take a picture of your solution.